Hey there, welcome to this video on rational functions, and today we're going to look how to find the domain of a rational function algebraically, as well as look at the average rate of change of rational functions. Alright, so let's go ahead and get to it. So first of all, we're going to talk domain of a rational function, and it's important to note from our previous lessons in rational functions, you know that the domain is all real numbers of a rational function. Except for where there is an asymptote, right? And a rational function has an asymptote wherever it's undefined due to the denominator being equal to 0. So if the denominator is equal to 0, that can't happen in math. That's what generates an asymptote. So what we're going to do is we're going to go ahead and set the denominator equal to 0. We'll solve, and then that's where we have a discontinuity. Then the domain is everything except for that discontinuity or that location. Okay, we will have to go ahead and write the domain in inequality and interval notation, but that is kind of straight up. Okay, so just to kind of summarize and highlight what we talked about here, we want to go ahead and determine the values of x for which the function is defined. And again, we do this by setting the denominator equal to 0 and solve the equation for x. Okay, and then just after that, all we have to do is write the domain using the specified notation. Okay, so here is our first example, and we are asked to find the domain of the function in inequality and interval notation. All right, well, if I want the domain, note this is a rational function due to having a polynomial over a polynomial. Okay, well, to find the domain, I more so care about what's the domain restrictions. So I'm going to take my denominator, x squared minus 3x, and I'm going to set that equal to 0. Right, and the whole idea here is that that cannot be 0. So I'm going to factor this. Well, that is x times x minus 3. Then I set each piece equal to 0 or not equal to 0, however you want to go ahead and look at it. Okay, and over here I'm going to solve. I'll add 3 to both sides. And I get x cannot be 3 and it cannot be 0. So what's going to happen is at 0, I'm going to have an asymptote. There's an asymptote, and at 3, I'm going to have an asymptote. Okay, so my domain is going to be everything except those values. So it's going to be from negative infinity to 0, 0 to 3, and 3 to infinity. Okay, so I'm just going to go ahead and summarize that. So the domain, okay, and first I'll do inequality. It is going to be x is less than 0, that's this piece, or 0 is less than x, which is less than 3. Okay, that's this piece, right? 0 is less than x, which is less than 3, or x is greater than 3, and that is this piece here. Okay, we can go ahead and also do this in interval, which is what they want. So that would be negative infinity to 0, union 0 to 3, union 3 to infinity. All right, again, just to summarize, find the discontinuities of the rational function. Where are the asymptotes going to occur? Okay, so I have a vertical asymptote at 0 and a vertical asymptote at 3. Therefore, we exclude them from the domain. So all real numbers except those values. Okay, let's go ahead and look at another example. Again, we're asked to find the domain. So I'm going to go ahead and take the denominator, x squared plus 4x minus 5, and I'm going to set it equal to 0. X squared plus 4x plus 5, set it equal to 0. Okay, well now I have to go ahead and factor this. So x plus 4, x plus 4, I have x plus 5, x minus 1. And then, due to the zero product property, I can go ahead and set each piece equal to 0, and then solve. Okay, and again, the whole idea here, I just set it equal to 0 and I solved, but really it can't be equal to 0. We don't want that to be equal to 0. This gives us our domain restrictions. So I have a restriction at -5, okay, and this happens to be a hole. Now, how do I know it's a hole? Well, look at the numerator here. If I go ahead and rewrite my rational function, x plus 5 over x plus 5 times x minus 1, right? These are going to cancel. That generates a hole. So I know that there's a hole there. And then at 1, there is an asymptote. Okay? So what's our domain? Well, I have all of this value from -infinity up to -5, -5 to 1, and 1 to infinity. Okay, so what is our domain? Well, our domain is x is less than -5, or -5 is less than x, which is less than 1, or x is greater than 1. Okay, and again, that's inequality. And then interval notation, -infinity to -5, union -5 to 1, union 1 to infinity. Okay, and again, remember, for these values here, I'm using parentheses because they can't be equal to those values. So I'm excluding them from the domain. All right? Okay, moving on. Here is a practice problem. Please pause the video. Go ahead, try this one. All right, hopefully you paused it. Hopefully you set the denominator equal to 0. You factored with difference of squares. Okay, excluding -6 and +6, giving us our domain. All right. Here's example 2. Please go ahead, pause the video, give this one a go. All right, hopefully you paused this one and did it, and you did not get thrown off by that denominator. It looks weird. You can still factor it with the GCF of x. Okay, set each piece equal to 0. And you get x cannot be equal to 0, and x cannot be equal to 5. All right, now we're going to go ahead and talk about average rate of change, which is something that you have done from Math 1 to Math 2. We're going to talk about Math 3, and guess what? You'll talk about it next year in calculus. So the average rate of change is the average change between y values for each unit of x over a specific continuous interval of a function, and that's very important. It has to be a continuous interval. With a rational function, I cannot go ahead and, let me pick a different color than blue. I cannot take a point here and a point here and say, okay, what's the average rate of change? Well, it's not continuous. I have a vertical asymptote there. So it just has to be a continuous interval. Okay, and that corresponds to the slope of a line through the 2 points, which we call a secant line. We'll talk more about secant values as we get to the end of the year. Here they have an example of the average rate of change over -8 to -5. So here is -8. Okay, well, here's the function value. Here is -5. Okay, well, here's the function value. And that change, right, from delta x, we increased +3 units, or sorry, +6 units, that's delta y. And then here our delta x is 3 units. Okay, so we're going to go ahead and calculate average rate of change. So how do you do that? Well, in order to find the average rate of change, you have to have the function values. So here's kind of step 1, and what you need to do is you need to find f of x1 and f of x2. Find the function values. Step 2, you're going to go ahead and just calculate the average rate of change. What is delta f over delta x? Rise over run, and I recommend writing that in your notes, right? It's rise over run. Maybe even this one helps too. Delta y over delta x. Super simple. Let's go ahead and look at an example. So in this example, it says the function d is equal to 50 over m, which represents the density in centimeters cubed over grams of an object with a volume of 50 cubic centimeters and a mass of m grams. Find the average change in the object's density from a mass of 5 to 16 grams. Okay, so step 1, I need to go ahead and calculate the corresponding function values over the interval. All right, so I'm going to write step 1. Okay, and I want d of, I'm going to say 16 grams. Okay, and then I'll also need what is d of 5 grams. So I go ahead and I just plug these into the function. So 50 over 16. When I plug this in, we get 50 over 5, which happens to be 10. Okay, and again, these are the densities in terms of cubic centimeters per gram. Okay, so there are my function values. Right, so now step 2, I'm going to go ahead and I'm going to calculate, okay, delta f, right? Well, in this case, what's delta d over delta x, which is m. So I have d of 16 minus d of 5 over 16 minus 5. Okay, so we can go ahead and we can plug this in. My delta, or my d of 16g is 50 over 16. Okay, minus, I'm just going to go ahead and leave it as, well, this one requires a calculator, so I'll put 10. Okay, and again, this is cubic centimeters per gram, and then down below we have 11 grams. Okay, so I'm going to go ahead and pick up my calculator. I'll do 50 divided by 16, which is 3.125. I'll subtract 10, giving me negative 6.875, and I'll divide by 11, which gives us negative 0.625. Okay, and as far as units, this is cubic centimeters per gram per gram. And then another way that you could write this would be cubic centimeters over grams squared. Okay, so just as far as units, a couple of ways that you could write this. All right. Okay, so we want to go ahead and answer in a sentence. So we'll say the average change in the object's density from 5 grams to 16 grams in mass is decreasing by 0.625 cubic centimeters per gram per gram. Okay, and there is your answer. Okay, and it's important to use that word decreasing or increasing. This will come up in calculus, but you want to state, is that average change going up or is it going down? Okay, and notice I didn't include that negative. That negative is told to me by decreasing. All right, here is a practice problem for you. Please go ahead, pause the video, and give this one a go. All right, hopefully you pause this. Your first x value is 10 units. Your second one is 50. So when you plug these in, you get outputs or function values of $5.03 and $1 and 0.0012 cents. So you plug this in, and then your delta C, which is cost, divided by your delta X, which is units, gives you your average rate of change. Okay, and there you have it. All right, that is it for this unit, or for this lesson and unit. This is the last lesson in the unit. We went ahead and we talked about how to find the domain of a rational function. Remember, find the discontinuities and then exclude those from the set of all real numbers. And then we talked about how to find average rate of change. Delta y over delta x, or delta function values, delta f over delta x. Rise over run. All right, catch you next time. Be safe, be easy.